Welcome to this complete lecture on wireless communication standards. Whether you pick up your phone on a train, stream video at home, or connect a smart sensor in a factory, you are using one of the 7 standards we cover today. 3G, 4G, 5G, 802.11n, AC, AX, and B. Let's break them all down. Before we dive into each standard, you need to understand one crucial distinction. All 7 of these protocols belong to 2 completely separate families, with 2 different governing bodies, designed for 2 different environments. On the left, cellular standards. 3G, 4G, and 5G. These are governed by an organization called 3GPP, the Third Generation Partnership Project. Your phone connects to towers owned by carriers like Chunghwa Telecom, Taiwan Mobile, or Far EasTone. This works everywhere you have signal, indoors, outdoors, or moving at 300 km per hour. On the right, Wi-Fi standards. 802.11n, AC, AX, and B. Governed by the IEEE 802.11 Working Group. You connect to an access point, a router that you own. It works up to about 300 meters. No carrier subscription required. They solve the same problem, wireless data, but through completely different architecture. Here is how these standards evolved over time. In 2001, 3G launched in Japan, the first time a mobile phone could access the real internet. By 2009, Wi-Fi got its first major upgrade with 802.11n, introducing multiple antennas for the first time. 4G LTE arrived in 2010, the all-IP revolution that made smartphones indispensable. 802.11 AC in 2013 pushed Wi-Fi into the multi-gigabit era. Then 5G in 2019, Wi-Fi 6 in 2021, both designed not just for speed, but for connecting thousands of devices simultaneously. And most recently, Wi-Fi 7, finalized in 2024, delivering speeds that rival wired Ethernet. 3G, the third generation of cellular networks. Launched in Japan in 2001, this was the moment mobile phones became something genuinely useful beyond voice calls. Peak theoretical speed, 42 megabits per second with HSPA+. Latency around 100 milliseconds. Operating in frequency bands between 850 and 2100 MHz. The core technology was WCDMA, Wideband Code Division Multiple Access. Instead of separating users by time slots or frequency, WCDMA gives every user a unique mathematical code. Multiple callers share the exact same frequency band simultaneously. The network untangles them using their codes. Before 3G, mobile internet meant WAP, Wireless Application Protocol. Slow, text-only, almost unusable. 3G brought real web browsing, video calling with 3GP format, and actual email. For the first time, the internet was in your pocket. And through successive software and hardware upgrades, HSPA and HSPA+, sometimes called 5G, speeds climbed from 7 megabits all the way to 42, without replacing the core infrastructure. That kind of graceful evolution became a template for future generations. Next, 4G LTE. This is the generation that made smartphones truly indispensable. Launched in Norway and Sweden in 2010, it represented a fundamental redesign of how mobile networks carry data. Peak theoretical speed of 1 gigabit per second with LTE advanced. Real-world latency between 30 and 50 milliseconds. That latency drop from 100 milliseconds to 30 milliseconds is what made real-time apps, navigation, gaming, video calls, actually usable on mobile. The key innovation was OFDMA, Orthogonal Frequency Division Multiple Access. 4G divides the radio spectrum into hundreds of tiny subcarriers. Each subcarrier is very narrow, making it resilient to interference and multipath fading. Different users get different subcarriers simultaneously. This is dramatically more efficient than CDMA. It's the same fundamental technology that powers your cable or fiber broadband connection. MIMO, multiple input, multiple output. 4G introduced up to 4x4 MIMO, meaning 4 antennas at the phone and 4 at the tower. Each pair can transmit a completely independent data stream at the same frequency. 4 streams, 4 times the data. This is spatial multiplexing and carrier aggregation. Your phone can simultaneously use multiple separate frequency bands as if they were one. 700 MHz for range, 1800 MHz for capacity, 2100 for speed, combined into a single pipe. More lanes, faster highway. Next, 5G, the most misunderstood generation. It is not just faster 4G. It is a fundamentally new architecture, designed from the ground up with three completely different use cases in mind. First, eMBB, Enhanced Mobile Broadband. This is what most people think 5G is. Streaming, augmented reality, virtual reality. Peak theoretical speeds reaching 20 gigabits per second. Second, MMTC, Massive Machine Type Communications. This is for the Internet of Things. 5G can theoretically support 1 million connected devices per square kilometer. Smart city sensors, agricultural monitors, industrial meters, all simultaneously, on the same network. Third, and this is where 5G gets truly revolutionary, URLLC, ultra-reliable low-latency communications. The target latency is less than 1 millisecond. That enables autonomous vehicles to react faster than a human brain. It enables a surgeon in Sydney to operate a robotic arm in a hospital in Melbourne, in real time. Now, and this is exam critical, 5G operates across three very different frequency ranges. Low band below 1 GHz, excellent coverage, hundreds of kilometers, but speeds barely above 4G. Mid-band between 1 and 6 GHz, the sweet spot used in most deployments, good speed, good range. And wave, millimeter wave, between 24 and 100 GHz. Multi-gigabit speeds, but the signal cannot penetrate a glass window. Remember, higher frequency always means faster speed but shorter range and worse penetration. That is the master rule of wireless, and it applies to every standard we discuss today. Now let's turn to the Wi-Fi family. All four standards we cover, 802.11n, AC, AX, and B, fall under the IEEE 802.11 umbrella. IEEE stands for the Institute of Electrical and Electronics Engineers. Each revision of the standard improves throughput, range, capacity, or efficiency in some way. The Wi-Fi Alliance, a separate certification body, gives these standards friendlier marketing names. 802.11n becomes Wi-Fi 4. 802.11 AC becomes Wi-Fi 5. 802.11 AX is Wi-Fi 6, or Wi-Fi 6E when it includes the 6 GHz band. And 802.11b is Wi-Fi 7. Look at this speed progression. Wi-Fi 4 topped out at 600 megabits. Wi-Fi 5 reached 3.5 gigabits. Wi-Fi 6 hits 9.6 gigabits. And Wi-Fi 7 reaches a theoretical 46 gigabits per second, roughly 75 times faster than Wi-Fi 4, in just 15 years. One important note before we go further. Wi-Fi speed is the speed between your device and your router, not your internet speed. That is still limited by your ISP plan. Let's look at Wi-Fi 4 and Wi-Fi 5 together, two standards that defined a decade of wireless networking. 802.11n, Wi-Fi 4, ratified in 2009. Peak speed, 600 megabits per second. The headline innovation was MIMO, multiple input, multiple output. For the first time, Wi-Fi used multiple antennas to send multiple independent data streams simultaneously. Think of it like going from a single-lane road to a 4-lane motorway. It also introduced dual-band operation, supporting both 2.4 GHz for range and 5 GHz for speed on the same device. Channel bonding doubled bandwidth by combining two 20 MHz channels into one 40 MHz channel. And frame aggregation bundled multiple packets into a single transmission, slashing overhead. 802.11 AC, Wi-Fi 5, arrived in 2013. Peak speed, 3.5 gigabits per second. Notice something, it dropped 2.4 GHz entirely, 5 GHz only. This was a deliberate engineering choice. 5 GHz has far less interference, no Bluetooth, no microwaves, fewer competing networks. The landmark addition was MU-MIMO, multi-user MIMO, for the downlink direction. Previous Wi-Fi took turns talking to each device. MU-MIMO allows the router to transmit to 4 devices simultaneously. 256 CAM modulation packed 33% more bits into every symbol. And channel widths grew to 80 and 160 MHz, a massive bandwidth increase. Between Wi-Fi 4 and Wi-Fi 5, the performance difference is roughly 6-to-1. That is the difference between buffering a 4K stream and watching it without a single pause. 802.11 AX, Wi-Fi 6 and Wi-Fi 6E. Ratified in 2021, this standard represented the biggest architectural leap in Wi-Fi since 802.11n. And the key shift was this. Instead of just making Wi-Fi faster for one device, 802.11 AX made Wi-Fi smarter for many devices at once. OFDMA, borrowed directly from 4G LTE technology. Wi-Fi 6 divides each channel into resource units, smaller slices that different devices can use simultaneously. In a home with 20 smart devices, instead of queuing up one by one, they all get served in the same time slot. Efficiency in dense environments improves dramatically. BSS coloring. This solved a major problem in apartment buildings. Previously, your Wi-Fi could hear your neighbor's router on the same channel and had to wait, even though it was not your data. BSS coloring tags each network with a number. Your device simply ignores signals from differently colored networks. The interference problem is solved at the protocol level. Target Wake Time, or TWT, is revolutionary for the Internet of Things. The router negotiates a precise schedule with each IoT device. Wake up at exactly this moment, send your sensor reading, go back to sleep. Instead of constantly scanning for a signal, devices sleep for hours or days at a time. A small temperature sensor on a coin cell battery could now last years. And then Wi-Fi 6E. Same 802.11 AX standard. The only difference is an additional frequency band, 6 GHz. Spanning from 5.9 to 7.1 GHz, this band has 14 additional 80 MHz channels. More importantly, it is completely empty of legacy devices. No 802.11b, G, N, or AC devices can use 6 GHz. It is a clean slate, and a clean slate means dramatically lower interference. Uplink MU-MIMO and 1024 QAM round out the improvements. Devices can now transmit back to the router simultaneously, and each symbol carries more data than ever before. 802.11b, Wi-Fi 7. Finalized in 2024, this is the cutting edge. And it introduces a feature so significant that it changes how we think about wireless networks entirely. The numbers first, 46 gigabits per second theoretical peak. Sub-millisecond latency target. Channels up to 320 MHz wide. And 4096 CAM modulation, encoding 12 bits into every symbol. Multi-link operation, MLO. This is the game changer. In previous Wi-Fi, your device chose one band and stuck with it. 2.4, 5, or 6 GHz, pick one. With Wi-Fi 7, your device can use all three simultaneously as a single logical connection. They appear as one unified link to your applications. If the 5 GHz band gets congested, traffic instantly flows to 6 GHz. No interruption, no reconnection, transparent, 320 MHz channels, double the maximum width of Wi-Fi 6. To put that in context, a single 320 MHz channel on Wi-Fi 7 is wider than the entire 2.4 GHz band that 802.11n used. This is only practical in the 6 GHz band, where there is enough clean spectrum to fit it. 4096 CAM encodes 12 bits per symbol, a 20% improvement over Wi-Fi 6's 1024 QAM. Combined with 16 spatial streams, doubled from Wi-Fi 6's 8, the theoretical throughput reaches 46 gigabits. That is faster than most data center storage systems. Wi-Fi 7 is designed to make wireless indistinguishable from wired. For AR, VR, cloud gaming, and industrial automation, that matters enormously. Here's the full comparison table. Take a moment to read across each row. Notice the color coding: blue rows for cellular, green for Wi-Fi. The first column is always the technical standard name. The second is the marketing name you'll see on packaging and advertisements. Look at the peak speed column. From 42 megabits for 3G to 46 gigabits for Wi-Fi 7. That is a 1,000-fold increase over 23 years. Each generation roughly doubled or tripled the previous. The latency column tells an equally important story. 3G at 100 milliseconds. 4G at 30 to 50. 5G targeting below 1 millisecond in standalone mode. Wi-Fi 7 also targeting sub-millisecond. We're approaching the limits of human perception, and the requirements of machine-to-machine communication. And frequency. Notice how cellular spans everything from 700 MHz all the way to 100 GHz. Wi-Fi is concentrated in 2.4, 5, and 6 GHz, unlicensed bands available globally without a spectrum license. The footnote at the bottom is important. 5G's 20 gigabit peak is theoretical. Real-world 5G averages 100 to 900 megabits depending on which band you are on and how your carrier has deployed it. Always distinguish theoretical peak from real-world performance. These are the 8 fundamental technologies that power every standard we have discussed. If you understand these, you understand why each generation performs the way it does. OFDMA, Orthogonal Frequency Division Multiple Access, splits a radio channel into many narrow sub-carriers, assigns different sub-carriers to different users simultaneously. It is the backbone of 4G, 5G, and Wi-Fi 6 and 7. MIMO, multiple input, multiple output, multiple antennas sending multiple independent streams. Standard MIMO tops out at 4BY4. Massive MIMO in 5G uses up to 256 antennas, beamforming each stream like an individual spotlight toward each device. Beamforming. Think of the difference between a light bulb and a torch. A traditional antenna broadcasts in all directions, wasting energy. Beamforming focuses the radio signal toward the specific device that needs it. Better signal, less interference for everyone else. QAM, Quadrature Amplitude Modulation. This determines how many bits of data you encode into each radio symbol. 64 QAM encodes 6 bits. 256 CAM encodes 8. 1024 QAM encodes 10. Wi-Fi 7's 4096 CAM encodes 12. Each step up is a roughly 20% improvement in throughput, but only achievable with a very clean, strong signal. Multi-link operation, Wi-Fi 7 only. Simultaneous use of 2.4, 5, and 6 GHz as one link. Traffic balances across all three. Congestion on one band is transparent to your application. BSS coloring eliminates inter-network interference in dense Wi-Fi deployments. Target wake time revolutionizes IoT battery life through scheduled sleep cycles. And network slicing in 5G creates multiple virtual networks, each with guaranteed performance levels, running on a single physical infrastructure. One tower, many networks. These are not isolated features, they work together. A 5G device might use OFDMA, massive MIMO, beamforming, and network slicing simultaneously on a single connection. Theory is important, but let's ground these standards in the real world. Where does each technology actually live? Autonomous vehicles need 5G URLLC. That sub-millisecond latency is non-negotiable when a car is making a braking decision at highway speed. Stadiums and dense venues use both. Wi-Fi 6 or 7 handles the indoor crowd. 5G mmWave can handle the open-air sections where cable infrastructure is impractical. Remote surgery requires 5G standalone, only SA mode achieves true sub-millisecond latency. Non-standalone 5G, which uses a 4G core, cannot meet this requirement. Rural IoT sensors, 5G MMTC, or 4G NB-IoT for areas without 5G coverage yet. Cloud gaming and VR, Wi-Fi 7 at home, 5G outdoors. Home networking, Wi-Fi 6E is the current sweet spot for most consumers. High-speed rail uses 5G sub-6, the mid-band travels far enough to maintain handoffs between towers at speed. Smart factories are moving to 5G private networks, a licensed slice of 5G spectrum deployed within the factory itself, with guaranteed latency for robotic arms and conveyor systems. In-flight internet uses Wi-Fi 6 in the cabin and satellite backhaul. Hospitals deploy Wi-Fi 6 for device density and 5G MMTC for the vast number of monitoring sensors. The pattern is clear. When you need wide area coverage and mobility, use cellular. When you need local density and low cost, use Wi-Fi. We have now covered 7 standards across 23 years of wireless evolution. And every single engineering decision in every single one of them traces back to one fundamental rule. Higher frequency equals faster speed, plus shorter range, and worse wall penetration. This is not a design choice. This is physics. And it is inescapable. 5G mmWave at 28 GHz delivers 4 gigabits per second, but it cannot penetrate a glass window. That is not a bug. That is physics. 5G SUB6 at 700 MHz covers an entire city from a single tower, but you are lucky to get 200 megabits. That is also physics. Wi-Fi 6E on 6 GHz, faster and cleaner than 5 GHz, but shorter range. 4G at 700 MHz rural, outstanding coverage across hundreds of kilometers. Wi-Fi 5 on 5 GHz, faster than 2.4, smaller coverage bubble. Every time you wonder why a wireless standard made a certain frequency choice, come back to this rule. It is the lens through which every wireless engineer sees the world. Let's bring it all together. On the cellular side, 3G gave us the first real mobile internet using WCDMA spread spectrum technology. 4G transformed mobile into an all-IP system with OFDMA and carrier aggregation. 5G introduced three distinct use cases: enhanced broadband, massive IoT, and ultra-low latency, along with massive MIMO, network slicing, and the new wave spectrum. On the Wi-Fi side, 802.11n introduced MIMO and dual band. 802.11 AC moved to 5 GHz only with MU-MIMO. 802.11 AX brought OFDMA, BSS coloring, and TWT to Wi-Fi, plus a new 6 GHz band with Wi-Fi 6E. And 802.11b, Wi-Fi 7, introduced multi-link operation, 320 MHz channels, and 4096 CAM. And the key difference: cellular is licensed spectrum, carrier-managed, and wide area. Wi-Fi is unlicensed, self-managed, and local. Both now achieve multi-gigabit speeds, but the architecture is fundamentally different. Modern phones use both simultaneously, seamlessly offloading from cellular to Wi-Fi when available. 3GPP governs cellular. IEEE 802.11 governs Wi-Fi. The Wi-Fi Alliance certifies products and gives us the friendly marketing names. These organizations will continue setting the standards for the next generation, and what comes after Wi-Fi 7 and 5G Advanced is already being discussed in working groups around the world.